Hi, welcome to Physics with Ms. Dahlberg. Today we're talking about simple harmonic motion. And to talk about simple harmonic motion, I guess the first thing we need to talk about is oscillatory motion. And so if we talk about oscillatory motion, that is any motion that repeats at a regular interval. And an example of that would be like a ball bouncing. It repeats at this regular interval. And we need to define something else. We need to define a period. And a period is the time for one complete oscillation or one complete cycle of that motion. And an example of that is the Earth going around the sun. That has a period of 1 year because it takes one complete year for that cycle, for that orbit. And so now let's go on to simple harmonic motion. Now, simple harmonic motion is oscillatory motion, but it has two requirements. For it to be simple harmonic motion, there has to be two things. The first, that object has to be moved by something called a restoring force. And secondly, the object will oscillate about something called the equilibrium position. And so let's define restoring force. Restoring force is the force that pulls an object back to its starting place. So if that force pulls it back to where it started, and it keeps on pulling it back to where it's starting, then it's a restoring force. Now we have a special name for that starting place. That starting place is its equilibrium position. And at that equilibrium position, that is the location where the net force is zero. In other words, if there's a force, they're balanced. So you're not going to have some kind of unbalanced force there. Okay, so let's look at an example of something undergoing simple harmonic motion. And a mass on a spring is a really good example of this harmonic motion. So I have several scenarios of this mass on a string, but here we go at position number 1. We have this mass hanging on a spring, and it's just hanging there. It hangs down to this dotted line, which is known as the equilibrium position. So this is the equilibrium position right here. And if we pull it down and stretch that spring, we have this energy added to the system to give it some maximum displacement. And when we let go, that spring will start moving, and it will move back up to the equilibrium position, and then it will keep on going and compress the spring, and then it will stretch back down to the equilibrium position, and then it will go past the equilibrium position down to this maximum displacement again. And so you have this harmonic motion, this cycle. And if we kind of draw a little graph of the motion, you notice we get this nice little curve in the motion, which we'll come back to in a minute. And so if we look over here at the equilibrium position, I told you that in order for it to be an equilibrium position, we have to have all the forces balanced there. And right here, we have gravity pulling it down, and that is completely balanced by the spring force, pulling it up. And so, so it meets that condition right there. Now, when we pull it down at this point, there is velocity is 0. It's not moving. But at this point, the force on this spring is at a maximum, which means the acceleration on this block is also at a maximum, and it's up. Now when it comes back up to 3, the forces are balanced again. The acceleration is 0, but the velocity is up. When it gets to the top, the velocity is 0 again. It stops it because we have the maximum force again. This spring is compressed. And because it's at that point where it's turning around, the acceleration is down. Here, we have this point where the forces are balanced again. It's at the equilibrium position. The acceleration is 0, but the velocity is down. It's moving down. And then here, the velocity is 0. That's the turning around point. The acceleration is up. That maximum spring force is going up. Now, if you look at the displacement, it oscillates between a maximum displacement here, and we call that the amplitude. And this is the amplitude. And down here, this is the amplitude. And if this is the 0 line, this would be positive A or negative A, depending on your direction. Okay. So let's look at that motion of something moving in simple harmonic motion. So we're going to go to these graphs, and we will look at these graphs in class and kind of work with these graphs. But let's kind of analyze one. Analyze one to start with. So if we look at this one, we have, this is a position time graph. So we have position versus time here. And we have the maximum displacement right here at this point, right up here. And we let go, and our little mass on the spring moves through the equilibrium position at 0, down an equal amount on the other side. So the amplitude of this is 10 and negative 10. And then it turns around and moves back up. And so if we traced that motion of our mass on a spring, we would see this for our position time graph. Now, if we look at that, we can translate that to a velocity time graph, similar to what we did earlier in the year. And if we look at that, if we look at this point right here, where you have maximum displacement, I want you to notice at this maximum displacement, we have a velocity of 0. At this maximum displacement, we have a velocity of 0. At this maximum displacement, we have a velocity of 0. And so at that point, the velocity is 0, but I'll do this in red. When we get over here, when we're at our equilibrium position, I'm going to do that in red. I'm put a little X there. If you notice right there, at the equilibrium position, the forces are balanced. So the acceleration is 0 down here. The forces are balanced. But look at the slope of this line. That thing is moving pretty fast as it moves from up to down. And so here it's at its maximum negative velocity right there. And in the next instance where it's at the equilibrium position again, you again have maximum velocity, but this time it's moving back up. And so we have the maximum positive velocity. Okay, and when it's at the maximum velocity, the acceleration is 0. Now if we go back and look at our, let me do that in green. If we look at our maximum displacement areas where the velocity is 0, the velocity is 0 here, but we have a pretty big acceleration. That is the point at which you have the maximum force from the spring and it's turning around. And so you have the most acceleration there. And so those graphs, we'll look at those in class and kind of talk about those a little bit more. Okay, which leads us to, here we have a mass on a spring again, except this time we have it turned sideways. So our spring would be coming right here. And this is right here. We're going to say that this is the equilibrium position. This is where x equals 0, our equilibrium position. Okay, and so if that's the case, this is our amplitude here. We'll label these A. We'll label those A, and so if we say this is positive A, this would maybe be negative A. Again, you can decide. Now, if we look at this, at the equilibrium position, the forces are balanced, so our acceleration is 0. But at the equilibrium position, if this thing is sliding back and forth here, the velocity at this point is at a maximum. And if we come over here, when we pull this back to this maybe starting position with maximum amplitude, at this point the force from the spring is the biggest, and so we have the acceleration is at a maximum because the force is at a maximum. But at this point the velocity is 0. Okay, and what you have here, you also have at this other side, which is also maximum amplitude. It's just the spring is stretched instead of compressed, but you have maximum acceleration, again, because the force is at a maximum. That spring is stretched the most it can go. And at this point, it's turning around again, and so the velocity is 0. Now, in simple harmonic motion, we know that the energy goes between kinetic energy to potential energy. During this whole transition. And so if we come back to this graph and we look at this, which point on that motion would it have maximum kinetic energy? If we look at that graph, we know the maximum kinetic energy is where the velocity is at a max. So at this point, we have maximum kinetic energy, and we know that that kinetic energy is 1/2, oops, mv squared. Now, when does it have maximum potential energy? And if we look at that, anytime it's at its maximum amplitude, the velocity is 0. All of that kinetic energy has become potential energy. And so since it's a spring, it's maximum elastic potential energy. And so we know that this equals 1/2 kx squared. And so we have a continual conversion between these two types of energy. And we're going to use that in these relationships.